So this is joint work with Nora, who is in the audience. I've been given to understand. So if you have further questions, you can ask her. Unless you want to fly to New York and ask me, then you could ask me. So this kind of starts with a long time ago with the question of Douglas Munn. So let S be an inverse semigroup with 0. So in this talk, every inverse semigroup has a 0 element and K is a field. Then the contracted semigroup algebra, which will just be called the semigroup algebra from now on, has basis the non-zero elements of S, and the product extends that of S. So I view the 0 of S as the same as the 0 of the algebra, which is what you should do. So for example, if I take S to be the semigroup of n by n matrix units Eij, together with 0, that's an inverse semigroup, and its semigroup algebra is n by n matrices over K. Again, because the 0 is identified with the 0 of the algebra, and since these guys are linearly independent, they basically, this is the semigroup algebra, and this is of course simple. By the way, if I did not identify the 0 of the semigroup with the 0 of the ring, then you would always have the trivial homomorphism to the field K, and so you would never get a simple algebra. So you definitely want to do this. So Munn observed in the 70s that if the semigroup algebra is simple, then the semigroup must be congruence-free. Congruence-free just means it has no quotients. You might want to call this simple, but because in semigroups you can talk about ideals, there's kind of a difference between having no ideals and no congruences. So we use the term congruence-free. So for instance, the finite congruence-free inverse semigroup are exactly these matrix units, inverse semigroups, and they have simple algebras. But Munn observed all the way back in the 70s that if you take the polycyclic inverse monoid, this is the inverse monoid generated by a bunch of orthogonal isometries X. So these are the guys which generate the Kuntz algebra. This algebra is simple if and only if X is infinite. And he identified the Levitt algebra as the unique simple quotient when X is finite. So, and he was of course completely unaware of Levitt or Kuntz's work. He just figured this out on his own. He also actually introduced in the same paper, he actually looked at a self-similar group action on an infinite alphabet in the 70s, even though he didn't define self-similar groups in general, but he actually writes one down, which was kind of interesting. So he is a bit ahead in this paper in the 70s, which is not so easy to find because it's in the conference proceedings. And I had to find somebody who's at the university where the conference proceeding was to find it in the library. So in any event, he posed the question of characterizing when a congruence-free inverse semigroup has a simple algebra. And from the way he writes it, I mean, I can't ask Munn anymore. He's not with us anymore, unfortunately. He is one of my real mathematical heroes. But you get the impression he expected a characterization that depended only on the inverse semigroup. You know, if your inverse semigroup was congruence-free and blah, 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 that should be the answer. And he proves in the 70s that if S is congruence-free, if it's 0 E unitary, actually he had something slightly more general than that. And if it has what's called what he called the strongly zero disjunctive semi-lattice of idempotence, then the algebra is simple. Okay, so in modern language, strongly zero disjunctive means every filter is tight in the sense of Exel. So he just wrote right down the condition that means all your filters are tight. So he sort of understood that if you have tight filter, if not every filter is tight, then you have a problem. So that's kind of what he realized from the polycyclic inverse semigroup, where the filters in over a finite alphabet, the tight filters would the filters, principal filters are not tight. Exactly. That's how you get the extra relation. So he somehow realized that in the 70s. Of course, he didn't use the language of filter or tight, but he wrote down a condition which is equivalent to this. The zero unitary condition is something which implies Hausdorffness. He actually had a slightly more general condition which implies Hausdorffness, but it wasn't the absolute condition that gives Hausdorffness. So he was really quite a bit on the right track. But in my opinion, the best way usually to deal with inverse semigroup algebras is to use groupoid algebras. So back in, I guess, maybe it was the 90s, Patterson associated to each inverse semigroup an ample groupoid, which he called the universal groupoid G of S. Here, I guess everybody knows ample means it's etale and it has a basis of compact open subsets of the Hausdorff unit space. And Patterson proved that the universal and reduced inverse semigroup C star algebras are the corresponding algebras for this groupoid. And so I introduced ample groupoid algebras over commutative rings to prove a semigroup analog of this. And I actually had already done this in the case of finite inverse semigroups a long time earlier, where you don't have to think very hard on how to define a groupoid algebra, because the groupoid's discrete for a finite inverse semigroup. And then I kind of realized the idea generalizes. So what is a groupoid algebra? I guess probably it's been spoken about. If you have an ample groupoid G, KG, my notation is different than everybody else. I like to use the same notation used for group algebras. The groupoid algebra is just the K-span of the characteristic functions of compact open bisections. And the product is the convolution. And even though the sum looks infinite, it's finite. If G is Hausdorff, this is just the locally constant mappings with compact support. And for us in this, it's very important in this talk, support means the preimage of 0. I don't take the closure. That's absolutely fundamental in this talk. By the way, feel free to interrupt me if you have any, questions or anything. Yeah, so remember, support in this always just means the preimage of 0. I don't close it. Okay, so here I'm going to have a bunch of groupoid notions, which are like which not everybody uses the terminology the same way. Hopefully one day it will uniformize. This is not one of the controversial notions, but what comes afterwards. So GXX is just the isotropy group at X. It's all the arrows of the groupoid that start and end at X. The isotropy subgroupoid is the union of the isotropy subgroups. And now we get to sort of the controversial notions. So G is effective if G0. So the unit space G0 is always open. And if it's the interior of the isotropy groupoid, then the groupoid is effective. The groupoid is called topologically principal if the points of trivial isotropy are dense in G0. And it's called topologically free if G0 is dense in the interior of the isotropy groupoid. So these are 3 related notions that are all different. And in any given paper, any one of these things can mean any of the other things. Because you see, because effective and topologically principal all imply topologically free. For Hausdorff groupoids, effective is equivalent to topologically free. And for second countable groupoids, topologically principal is equivalent to topologically free. So if you live in the world of second countable Hausdorff groupoids, these 3 things are the same. And so what happened is that the terminology is bifurcated and people kind of use them kind of interchangeably. And so that's why you have to be careful when somebody uses these terminologies to make sure what they're talking about, because these things all diverge if you leave the world of second countable Hausdorff groupoids. Okay, so some less controversial notions. The orbit of an element X are just everybody you can get to from X by an arrow. And the groupoid's minimal if every orbit is dense. This terminology comes from group actions, of course. So we have examples in our paper, other people probably have them too. There are minimal Hausdorff ample groupoids that are effective, but not topologically principal. So if you go out of the second countable world, even if you're Hausdorff, topologically principal is not the same as effective. We also have minimal ample groupoids that are topologically free, but not effective. These examples above are groupoids associated to self-similar group actions over possibly infinite alphabets. We also have minimal non-Hausdorff universal groupoids of congruence-free inverse monoids that are effective but not topologically principal. So remember, we want to know when is the algebra of a congruence-free inverse semigroup simple. And there are examples of these things which are effective but not topologically principal. So we have to deal with the non-topologically principal case. Okay, so simplicity of Hausdorff groupoid algebras is now quite an old topic in the subject. The first result on simplicity of ample groupoid algebras was in the Hausdorff case and inspired by results in C-star algebras. It was in the paper Brown, Clark, Farthing, and Sims from 2014. In the original paper, they did things over the field of complex numbers, but it's very easy to modify their proof to make it over an arbitrary field. So if you have a Hausdorff ample groupoid and K is a field, then KG is simple if and only if G is minimal and effective. So notice depends only on the groupoid, not on the field. So from this, I was able to deduce in 2016 that if S is a Hausdorff inverse semigroup. So what does a Hausdorff inverse semigroup mean? It means its groupoid is Hausdorff, but you can write this down in purely semigroup theoretic terms. It means that in the natural partial order on the inverse semigroup, the intersection of finitely generated lower sets is finitely generated. So the lower sets are kind of coherent. So then Ks is simple if and only if S is congruence free, and it has this extra condition that Munn stumbled on, that the idempotents are strongly zero disjunctive. This just means that every filter is tight. I mean, we now know from Exel's work that there's a closed invariant subset consisting of the tight filters. So the only possible way that the universal groupoid can be minimal is if every filter is tight. So Munn sort of realized that this was a good condition to impose, but I don't think he knew it was necessary because the tight quotient wasn't invented yet. But anyway, Munn was very close to this case. He at least one of the directions. And these descriptions don't depend on the field. But sometimes you have to move on beyond Hausdorff. And in 2016, Nekrashevych and independently Clark, Exel, Pardo, Sims, and Starling in 2019 arrived at a similar but not exactly the same approach for the non-Hausdorff case. So I put CEPSS because it's too many names to fill my slide. So they defined, their approach is really the one that generalizes better than the Nekrashevych approach, but for the class of topologically principal groupoids, they're equivalent. So they defined a function to be singular if its support, remember again, support does not take a closure. Support is the inverse image, is the set of things which do not map to zero. So a function is singular if its support has empty interior. For instance, if you have a locally constant map, then its support always has non-empty interior unless it's a zero mapping. So you don't have any singular mappings in the Hausdorff case. And the singular functions they prove forms an ideal. And Nekrashevych defined essentially the same ideal for topologically principal groupoids in a slightly different formulation. But you can check it's the same ideal in the special case of a topologically principal groupoid. And they proved that if G is topologically principal and K is a field, then Ks is simple if and only if G is minimal, and this ideal of singular functions vanishes. So this gives a characterization for topologically principal. In the second countable case, effective, which we know to be a necessary condition, implies topologically principal. So in the second countable case, this is kind of general. But as I pointed out before, you have examples of non-countable inverse semigroups, uncountable ones, which have effective groupoids which are not topologically principal. So it doesn't quite answer Munn's question. So unfortunately, the world changes a lot when you go to the non-Hausdorff world. And in the CEPSS paper, they gave the first example of a groupoid for which simplicity is field dependent. So in other words, unlike the Hausdorff case, the field matters. And I think this is probably a surprise. And what they did is they took the Nekrashevych algebra of the Grigor-Chuk group. So probably somebody's talked about self-similar groups. I don't know if anyone's talked about Nekrashevych algebras. I'll say more about them later in the talk. But if you take the Grigor-Chuk group, its Nekrashevych algebra has a simple algebra over all fields except those of characteristic 2, and it does not have a simple algebra over characteristic 2. That was shown in the CEPSS paper. And this is an example of an ample groupoid algebra for a non-Hausdorff groupoid. So, I mean, you can define it by generators and relations, but it is an ample groupoid algebra. This is kind of getting ahead of the story, but using our results on simplicity, Nora and I went a bit further. If G is a contracting self-similar group, I won't explain what that means, but the Grigor-Chuk group is a canonical example. Then we proved that either the Nekrashevych algebra of G is simple for no fields, or it's simple for all fields except those of finitely many positive characteristics. So for a Nekrashevych algebra of a contracting group, either it's never a simple algebra or it's simple except for finitely many exceptions, like was the case for the Grigor-Chuk group. And we also have an algorithm, which if you hand somebody the nucleus, which is a certain automaton which generates the group, outputs which fields it's not simple for. So we can algorithmically tell you, whether you have a simple algebra or not, which fields you get a simple algebra for. And we did this using our results about simplicity for etale groupoid algebras. So in any event, topologically principal is not really enough. because notice the result I just spoke about doesn't even recover simplicity, the simplicity result for the Hausdorff case. The Hausdorff case, the result was minimal and effective, but effective is totally independent of topologically principal. There are minimal effective Hausdorff groupoids in which every isotropy group is uncountable. So it's very far from topologically principal. Let me just point out that the universal groupoid of a congruence-free inverse semigroup with strongly zero disjunctive, that's that weird all filters are tight condition, is always minimal and topologically free. There are uncountable non-Hausdorff congruence-free inverse semigroups with effective groupoids that are not topologically principal. So to answer Munn's question, we have to go further. The previous results really only covered countable things. And so there's more to do. So now I'm going to talk about something called the essential algebra. It's a little bit strange because the essential algebra didn't exist when we first put our paper on arXiv, but by the time we got our referee report, it existed, and the referee suggested we look at it, and the referee's suggestion was very intelligent. So the essential algebra of an ample groupoid. So if G is an ample groupoid and K is a field, you can factor out by the ideal of singular functions because it's always there and it's a nuisance. And then you get something called the essential algebra. And this terminology comes from Biazniewski, I'm not quite sure how to say it, and Ralph Meyer for C-star algebras. So they introduced it sometime in between when our paper first came out and when we got our referee's report. And the referee suggested maybe we should really be looking at simplicity of the essential algebra. And so we proved this result. If G is an ample groupoid and K is a field, then the essential algebra of G over K is simple if and only if G is minimal and topologically free. So notice, again, this no longer depends on the field. It's the singular ideal that made things field dependent. If you're willing to go to the essential algebra and kick out the singular functions, then you just get to minimal and topologically free. Remember, topologically free is this condition that the unit space is dense in the interior of the isotropy. And also, moreover, if G is minimal and topologically free, this is actually the unique maximal ideal of the groupoid algebra. So not only is that guy simple, but there are no other maximal ideals. It has a unique maximal ideal. And so simplicity of the essential algebra is field independent, like I just said. And in their paper, Yevsky and Meyer showed that basically the same characterization characterizes the C-star, essential C-star algebra being simple, where the essential C-star algebra looks at a C-star variation of the ideal of singular functions. So it was suggested by the referee that maybe this would be true from what we proved, and then it was easy to modify our results to prove this. So batting back to our original results, which was about groupoid algebras and inverse semigroups. So our main result is that G is an ample groupoid and K is a field. Then KG is the algebra is simple if and only if G is minimal, topologically free, and the ideal of singular functions over K vanishes. So we don't need topologically principal. We just need topologically free, which is a necessary condition, unlike topologically principal. And this does recover the Hausdorff result, because remember, topologically free is the same as effective in the Hausdorff case. This is field dependent because of the ideal of singular functions depends on the field, as we saw with the Grigor-Chuk group. So how much does it depend on the field? So the first thing is it depends only on the characteristic of K. So simplicity over the complex numbers, real numbers, or rational numbers, it's all equivalent. This was really a fun thing to do because it's one of the few times in my mathematical life where I had to use Galois theory. So this relies on a descent argument. It's easy to see if you have singular functions over a small field, then you get them over a big field. But if you have singular functions over a big field, you have to use descent, which is a number theoretic technique to get down to a small field. And so we have to use the absolute Galois group, and it's kind of fun. It's not that difficult, but kind of fun since I never do this stuff. Simplicity, another thing we showed is simplicity in positive characteristic implies simplicity in characteristic 0. So if you have any singular functions over characteristic 0, by kind of, choosing, you can, by being somewhat clever, you can push things into positive characteristic at any prime you like and still have something, bad. So, because remember, once it's in characteristic 0, once it's not simple, it's already true over Q, and you can clear denominators and play games like that. We also prove for any set of primes P, there's a congruence-free inverse semigroup S so that the semigroup algebra is simple if and only if the characteristic does not belong to P. So what this is kind of saying is that 2 is the only constraint. Simplicity in characteristic, positive characteristic gives it in characteristic 0, but that's basically all you can say. All other primes are totally unrelated to each other. We also gave an example of a congruence free inverse semigroup whose filters are all tight, but the algebra is not simple over any field. So, so this condition which Munn stumbled upon in the Hausdorff case is not enough in the non-Hausdorff case. It doesn't, you might still not be simple over any field. And all these examples are constructed from self-similar group actions over infinite alphabets. We work with infinite alphabets so that the inverse, so that we don't have to deal with the Kunz-Krüger relation. So that way we can get an inverse semigroup instead of a groupoid. I mean, instead of an algebra, a Nekrashevych algebra. So that's the reason why we work with infinite alphabets. So I do want to say something about our methods. So even though I said the right way to study inverse semigroup algebras is via groupoids, in the end of the day, we end up going back to inverse semigroups. So if G is an ample groupoid, then it has this Boolean inverse semigroup S of compact open bisections. And the groupoid algebra is the quotient of the semigroup algebra by the ideal generated by saying that U plus V is the same as U union V whenever U and V are disjoint compact open subsets of G0. So I guess I first had this in my original archive preprint for the Hausdorff case, but it didn't make the final version of the paper. The non-Hausdorff case, Buss and Meyer came up with the proof that they sent me by email that they never published, but we put one in our paper anyway, slightly different proof. But and the tight, and this ideal here is the tight ideal in the sense of Excel for this inverse semigroup. So if you do this tight quotient, you get the groupoid algebra for a Boolean inverse semigroup. And the singular ideal of, I should have said the singular ideal of G rather than S. The singular ideal of G can be defined purely in an algebraic fashion inside of the semigroup algebra. So sorry, that should be a G. That was a typo. And you can also read off topological freeness and minimality algebraically as well. And in some sense, our study of simplicity has some elements in common with Douglas Munn's original approach back in the 70s. It's more complicated, but some of the ideas are not so dissimilar. So suppose S is now an inverse semigroup. It doesn't have to be Boolean with semi-lattice of idempotence E. Then our key observation or our key definition is we define an element of the algebra to be singular if given any non-zero idempotent, there's a smaller non-zero idempotent which annihilates A on, say, the right. So what it's saying is that the idempotents which annihilate A are dense in a certain sense. You cannot, no matter how small you go, you can always find a smaller idempotent which annihilates A. And that condition is actually left-right dual. And from there, you can get that these elements form an ideal, which we call the singular ideal. And this is just corresponds to the singular functions on Excel's type groupoid for S. So you can prove that these are precisely the list to Ks of the singular functions. But this is a very simple algebraic definition. There's no topology here anymore, right? We're just saying an element singular if no matter how small an idempotent you choose, as long as it's not zero, you can find a smaller non-zero idempotent which annihilates it on whichever side you like. And it turns out when S is a congruence free inverse semigroup, then this is the unique maximal ideal on the inverse semigroup algebra. Okay, the other definition I need, which corresponds to topological freeness, is what we call quasi-fundamental. So this is for the semigroup people in the audience, because I know there are some. So back in the 70s, Munn defined an inverse semigroup to be fundamental if the centralizer of the idempotence is the idempotence. So this is the semigroup version of being an effective groupoid. The interior of the isotropy is exactly the centralizer of the idempotence in the inverse semigroup associated to a groupoid. So this fundamental condition is exactly the effective condition in the language of semigroups. And Munn proved the uniqueness theorem that you would expect for groupoid algebras in the inverse semigroup language. He proved that for fundamental inverse semigroups, a homomorphism is injective if and only if it's injective when you restrict it to the idempotence. Or said semigroup theorists say that basically this means that the identity is the largest idempotent separating congruence. But anyway, this is really what he proved. So we're going to weaken this to something called quasi-fundamental, which is maybe a terrible name, to be the condition that every non-zero element in the centralizer of the idempotence is above a non-zero idempotent. So what this says is the idempotents are dense in the centralizer of the idempotence. Remember, topologically free means that the unit space is dense in the interior of the isotropy. The centralizer of the idempotence is the inverse semigroup version of the interior of the isotropy. And so this is the semigroup version of the density of the unit space. The idempotents are like the unit space. And for the inverse semigroup associated to a groupoid, this is the topological freeness thing. For those who like Munn representations, for the semigroup people, this condition means that if two non-zero elements are identified in the Munn representation, then they have a common lower bound. But anyway, that's for the semigroup people. Okay, so our main result at the end of the day for our simplicity theorem is a uniqueness theorem for quasi-fundamental inverse semigroups. So that's like topologically free guys with this technical condition of a zero disjunctive semilattice of idempotence. I'm not going to define it, but let me just tell you, every Boolean inverse semigroup has a zero disjunctive semilattice of idempotence. So if all you care about are Boolean inverse semigroups, you can ignore this condition. And being congruence free also makes you have a zero disjunctive semilattice of idempotence. Roughly what it means is that you can kind of use tight filters or ultra filters to distinguish idempotence. Zero disjunctive semilattice means you have enough ultra filters to separate kind of points from zero. That's kind of the idea. So the uniqueness theorem we proved, and this is our main technical result, is that if S if S is this quasi-fundamental inverse semigroup with this weird but minor condition on its idempotence, then the singular ideal is the largest ideal which does not contain any non-zero idempotence. So this is like your typical uniqueness theorem, C-star algebra theory. You want to say that any ideal bigger than your special ideal hits an idempotent. And so, of course, if you throw in minimal, then any ideal which is bigger than the singular ideal is going to contain an idempotent. And then using minimality, once you have one idempotent, you get everything. So this is really the key result. And then minimality immediately lets you go from here to say that any ideal which is not contained in the singular ideal will have an idempotent, and then using minimality, you can pick up everything. And so in particular, every non-zero ideal of the essential algebra really contains a non-zero idempotent of S. So that's the moral of the story. Okay, so now I'm going to turn to something completely different, which is still joint work with Nora, which is our sequel to this paper. I think I still have time. So we then decided we were going to try to use this natural algebraic characterization of singularity, which is, I think, easier to get your hands on for some examples than the topological description. So we use that to study Nekrashevych algebras of self-similar groups. So I'm going to say a little bit, but not a lot about this. I don't know what talks have been going on, so I'm kind of hoping somebody talked about self-similar groups. If not, I apologize because I'm not going to define them. Has maybe somebody said something about them?
Nope.
Nope.
Nope. Oh my. Oh well. That's what you get for not being there in person. Okay, let's see. Well, then I'm not sure how much this is going to make sense, but I probably have some other slides somewhere which introduce them. Okay, well, if you know about self-similar groups, then this might make sense, might make more sense than the previous slides. And if you don't, then I guess it won't. Let's see, can I write on the screen in some way? Is this like visible?
Yes.
Yes.
Okay, so a self-similar group is a group that acts on a regular rooted tree in such a way that the action of the group reflects the self-similarity of the tree. So for instance, by element G, it might flip these two trees. If I do that, this tree is going to go to this tree. And since these trees are kind of canonically isomorphic, if I label that things by the alphabet, this will be given by some automorphism of the tree, which I'll call G restricted to 0, because this is the node 0. This is the node 1. This is my alphabet here is 0, 1. And similarly, this tree is going to move over here. by some other automorphism of the tree once we identified the two trees called G restricted to 1. And the self-similarity condition says that these restrictions should also belong to my group G. So in general, when you restrict in general, if you have a group of automorphisms of this tree, there's no reason these restrictions or sections, they're called, have to belong to your group. But to be a self-similar group, they should be. And also we assume the action's faithful. Okay, so I hope that's enough of an introduction. I apologize, I somehow assumed somebody would have talked about this already, but maybe somebody will talk about it later. And then this talk will make sense retroactively, and you can watch the video. All right, that was drawing with my finger on. I'm glad I finally got the desktop with the writable screen. Okay, so I always assume I have at least 2 letters. Oh no, I'm still on annotate. I got to figure out how to turn that off, or I can't switch my slide. All right, fine. So the Nekrashevych algebra of Gx is the star algebra over K, whose generators are your group and the letters X, and they're stars because it's a star algebra. And you have some relations. The first relation says y star x equals delta xy. So it says that basically x and y are orthogonal isometries. So x star x is 1, y star x is 0, and y is not x. You should think of x as add the letter x to the beginning of a word or an infinite word, and you should think of y star as remove the letter y. If I put on the letter x and I remove the letter y, I'm going to get garbage unless y is x, in which case I'll get back to where I started. The second relation says that the sum of the is the Krieger relation. It says that the sum of the xx stars is 1. This just says if I remove the letter x and then I put the letter x back, that's the identity, since every word does start with some letter. And I also have relations which are the multiplication table of G, because my group is supposed to be here. Then I have a third relation which says I can, if I try to multiply a group element times a letter, I can apply the group element to the letter because it's acting over this alphabet, which you can think of as being the nodes on that tree. And then I do the section there. Okay, so G, oh, I don't have my annotation on anymore. So remember, so here I have my letter X, and then here I do Gx. And so what it's saying is if I do G times X, that's the same as G of X might be over here. And so G of X is now some new letter over here, and then I multiply it by that section. Okay, so that's I think that's all the relations. If I didn't forget anything, I'm just trying to figure out how to clear this. Okay, let's see, can I get the screen to move on? Okay, so inside of this algebra, you have the things of the form word, group element, and inverse word. And this is, and you have 0 as well. And this is a congruence free inverse semigroup, as long as I have 2 letters in the alphabet. So as an example, if G is the trivial group, this is the polycyclic inverse semigroup that Munn looked at. And Munn did look at some examples like this over infinite alphabets. And NKGX is the tight algebra of this inverse semigroup in the sense of Exel. This relation gets thrown in by the tightness thing. And it turns out that the singular ideal is the kernel of the natural representation of this on infinite words. What is the natural representation? Well, a self-similar group naturally acts on infinite words because infinite words are the ends of this regular rooted tree. So if I look at the infinite paths in this tree, those are infinite words, and the action of the group on the tree gives an action on infinite words. The letter X acts on an infinite word by putting that letter at the front of the word. You can think of this like infinite word as a stack, and you're just pushing the letter X on the top of the stack. And the star guy, you should think of as pop. Y star would pop the letter Y from the beginning of your infinite word if it starts with the letter Y. Otherwise, it gives 0 because it's garbage. And this is a representation, and it turns out the kernel of this representation is exactly the singular ideal. It's the only example I know where we have a very concrete description of the singular ideal. And the proof of this is a surprisingly clever thing that I'll give Nora 100% credit for, because it was really her idea. And so this algebra is simple if and only if the representation is faithful. If this representation is faithful. Okay, so I just want to give some examples, but again, if you haven't seen these before, it might go by a bit quickly. Okay, so let P be a prime number, and let F be a polynomial over Z mod P. That's not the p-adic integers, that's Z mod P, of degree n greater than 0 with non-zero constant term. And let MF be the companion matrix of F. Because the constant term is non-zero, this is an invertible matrix. So Zohr and Synek defined a self-similar group over the alphabet Z mod P, which is generated by the cyclic permutation that adds 1 to the first letter mod P. So that just means it cyclically permutes all the trees hanging down from the root. And then there's a copy of Z mod P to the n that acts in the following way. It fixes everybody in Z mod P to the n fixes the first letter of a word. The section at 0 is you multiply your vector v and zp to the n by this companion matrix. Your section at the very last letter is you just do sigma to the last input here, and then you do the identity at every other point. So I'll try to draw a picture of this. Oops, I don't know, I just hit some totally wrong button. That was bad. Okay, let me see, what did I do? Oh my. No, I totally hit the wrong button, and now I can't see my slides. I guess you guys can't see my slides either, right? Or can you still see them?
No, we
I somehow
can't see you.
Yeah, I was trying to hit the annotate button and I hit a wrong thing. So the way this Z mod P thing works is here I multiply by, here I have this guy V, I multiply it by the companion matrix. Here I take his last entry, Vn, and I do sigma to the Vn, and every place else I just do the identity. Maybe it's not so important. Anyway, these are famous self-similar groups introduced by Synek. These are contracting self-similar groups. So for instance, if you take the polynomial 1 plus x squared, you get the Grigor-Chuk group. And if you take x squared plus 1, you get a group called the Grigor-Chuk-Oechsler group. And if you take these particular, your prime to be 3 and x minus 1, you get something called the Fabrikowski-Gupta group. So if you choose your favorite polynomial, you'll get a group named after something. So these are all famous groups, and Synek constructed these as kind of the close cousins of the Grigor-Chuk group. And this kind of tells you the Grigor-Chuk group is natural, because this polynomial 1 plus x squared is the first polynomial you would ever think of over Z mod 2. Why? Because it's the minimal polynomial of the generator of the 4-element field, and it's the unique one. So this is the unique polynomial, which is the minimal polynomial of a primitive element of the 4-element field. And that's the kind of element you want to get an interesting group. Okay, and so Synek gave necessary and sufficient conditions for this to be a P group of intermediate growth like the Grigor-Chuk group. So using our methods about simplicity, we were able to prove that if you take one of these Synek groups of degree n, if the degree of the polynomial is 1, then this algebra, Nekrashevych algebra, is always simple for whatever field you like. If n is greater than 1, it turns out that if n is greater than 1 and the companion matrix acts transitively on projective space. So projective space is just all the lines in Z mod P to the n. So you just identify any two vectors differing by a non-zero scalar. If MF acts transitively on this projective space, then you get a simple algebra over every field except those of characteristic P. This is what happened with the Grigor-Chuk group. And if this guy does not act transitively, then the Nekrashevych algebra is never simple over any field. So for instance, and also Synek, if this thing acts transitively, then Synek's theorem tells you it's a P group of intermediate growth. So for instance, the Grigor-Chuk group, the action is transitive because what the action is, the companion matrix is just basically take the 4-element field. The 4-element field is a vector space of dimension 2 over the 2-element field, and the companion matrix is multiplying by the primitive element of that field, the generator. And so it actually acts transitively on all the non-zero vectors, not just on the lines. And so you get this transitivity property. On the other hand, the Grigor-Chuk-Oechsler group, the companion matrix of x squared plus 1, this is actually the transposition permutation matrix. And this permutation matrix fixes the vector 1, 1. So it does not act transitively on the line. And therefore, this algebra is never simple. This was already observed by Nekrashevych. We independently, or maybe Nora independently, observed this before we found out from Enrique that Nekrashevych already knew this. So, anyway, this gives kind of a uniform explanation for this stuff. I think I have one last slide. So we wanted to kind of go beyond just one prime. So we looked at a unique-like group. So let n be at least 2, and take these two matrices. These two matrices, of course, are quite famous. Let Gn be the self-sum group with alphabet Z mod n. Now n is no longer a prime. Generated by sigma, which adds 1 to the first letter mod n. So it just cyclically permutes the trees hanging under the root. And we have a copy of Z mod n squared, which acts as follows. So it's going to fix the first letter of a word. The section at 0 is multiplied by the matrix A, and the section at 1 is multiplied by the matrix B. The very last section is raise sigma to this second coordinate power, and you don't do anything anywhere else. It's like the unique group, but the point is we throw in these two matrices which generate SL2 Z mod n, because these two matrices act transitively on Zn mod the group, Zn squared mod multiplication by a unit. So on the kind of projective space. So this does the right thing so that we're able to prove this is a contracting group, and we're able to prove that the Nekrashevych algebra of G n is simple if and only if the characteristic of K does not divide n. So now if you want to give me any finite set of primes, you take n to be the product of that set of primes, and this will give you a group which is simple over fields of all characteristics except that finite list of primes. So there's no like special primes, basically any bad behavior you could hope for can happen. So let me just end with some open questions. Can we characterize the congruence-free inverse semigroups with a simple complex algebra? At least that's not field dependent anymore because I fixed the field. So maybe this is some semigroup theoretic property. What is it? Similarly, can we characterize the ample groupoids with a complex algebra? That's simple. Again, the complex algebra is the easiest one to be simple. As soon as it's simple over some field, it's simple over the complex. So that makes sense to do. Does there exist an amenable ample groupoid whose complex algebra is simple, but the C-star algebra is non-simple? You need the complex algebra to be simple for the C-star algebra to have a chance, but we don't know about the converse as far as I know.
Which
obviously your groupoid should not be
algebra is
Hausdorff. Sorry?
Which groupoid C-star algebra is that?
Well, I made it amenable so that it doesn't matter.
Could it also, but
I don't
if
mean
the groupoid-
essential.
if
I
the
mean
groupoid is not
reduced
Hausdorff,
or
there can be a
universal.
there can be a distinction between the reduced and essential. So
Yeah, no, I mean reduced or universal, not essential. Essential, we know when it's simple. Yeah, non-essential. I mean the standard reduced equals universal, not the essential. The essential we know when it's simple, and it's simple exactly when the complex essential is simple. So this is really about the original groupoid algebra, not the essential. Okay, so not the essential, but the old-fashioned ones. Just a random question: can you decide simplicity for Nekrashevych algebras for general automaton groups? For those who know what these are, and this is something I'm interested in. Is there always a natural representation so that the singular ideal is the kernel? One of the disadvantages of using the essential algebra is that in order to define representations, you need to check. It's easy to define them for the groupoid algebra. You can just use, bundles or sheaves or whatever. But then you have to check whether the singular ideal kills your representation, and that doesn't always seem to be easy to do. So it'd be nice to somehow have a natural representation. So for the Nekrashevych algebra case, we did. But we somehow use things our proof uses things that are somewhat specific to that situation. So it's not so clear that if you define the analogous representation for a general groupoid, whether it works. Because we definitely use some things that are specific to the setup there. I mean, the tight space is the same as the ultrafilter space, and it has a very nice form. It's a Cantor set and blah, blah, blah. It's somehow a bit special. And I guess that's all I have to say.